Okay, so in this video we're going to have a quick look at how a loudspeaker works. Now this follows on from the work that we were doing a couple of weeks ago about the motor effects. So you might remember this demonstration I showed you here. We've got a piece of foil connected to a power supply and we've got a magnet surrounding foil. Now nothing happens to the foil until we switch the current on. When we switch the current on, you might remember that I could make the foil move upwards, or if I reverse the direction of the current, or if I reverse the direction of the magnetic field, I could make the foil move downwards. So the direction of the force was affected by the direction of the current and the direction of the magnetic field. So that led us on to looking at Fleming's left-hand rule. Now this is just a way of quickly working out which way the force is going to act if you know the direction of the current and if you know the direction of the magnetic field. So what we do here is the thumb and the first two fingers of your left hand at 90 degrees to each other. Your first finger lines up with the direction of the magnetic field, your second finger lines up with the direction of the current, and then your thumb is going to be pointing in the direction that the force is acting. So it's just a quick and easy way to work out the direction the force is going to be in if you know the field and if you know the current. Okay, and we then develop that idea into how we can make a coil rotate around and how we could be a bit clever with this device here called a split ring commutator, so that those forces were the right way to keep the coil spinning around all the time. So we had a little look at a little demonstration, but obviously real motors come in lots of different shapes and sizes. Some of them are much bigger, but the point of this video is to focus in on how the same idea makes a loudspeaker do what a loudspeaker does. Okay, and obviously the loudspeaker, the idea of a loudspeaker is an electrical signal gets turned into a sound, whether it's the sound of music or the sound of someone's voice, whatever it is. Okay, so we're going to have a little look at that. Now the key difference with a loudspeaker is that the magnet involved is rather different. So at the back here there is a magnet, and that magnet, if we were to look at it head on, it would look like this. So there's a central north pole in the middle, then there's a gap, and then there's a ring of material all the way around it, which is a south pole. So that's what it would look like from head on. Over here, this is what it would look side on if we were to cut it in half. So there's our central north pole, and there's part of the ring that's the south pole all the way around the north pole. Okay. Now again, we have a coil of wire, okay, and that coil of wire just sits around that north pole in between it and the south pole, okay, and the electrical signal, I've just drawn that little wave there as the electrical signal, so it's an alternating signal. It doesn't stay in the same direction all the time, it changes direction, okay. Now what that means is, because the current going through the coil changes direction, the force acting on the coil is also going to change direction. Okay, we don't need to get too complicated about working out which direction it's going in, but it's enough to say that if the current's going through the coil in one direction, it's going to feel a force that moves it outwards, and if the current's going in the other direction, it's going to feel a force that pushes it back inwards. Okay, so if the current is changing direction all of the time, that's going to create a force that changes direction as well and makes that coil move in and out. Now if the current changes direction quickly, obviously it will move in and out faster, and if the current changes more slowly, then obviously it will move in and out more slowly. Right, so I'm just going to take that away, because what happens in real life is that this coil is attached to a paper cone. Okay, so all of that sits there. So what happens? An alternating current flows through the coil. When the current's in one direction, the coil feels a force that moves it outwards and the cone goes with it. When the current reverses direction, the coil feels a force in the opposite direction, moves back in, and the coil goes with it. So as the coil vibrates in and out, so does the cone, and the cone then pushes the air and sets up a sound wave. Okay, and the frequency of that sound wave depends on the frequency that the coil is going in and out at, which in turn depends on the frequency that the electrical signal is changing with. So different electrical signals can produce different sounds, and this is how your loudspeaker reproduces music, reproduces the sound of human voice. Okay, so this is a little video clip I recorded in school, and this is a loudspeaker that I took apart so you can see the paper cone and you can see the paper cone vibrating as the current oscillates in and out. Okay, so I've got it set on a very low frequency so you can actually see the paper cone moving in and out. If we go around the back now, you can see the back of the cone. So here's the magnet in here. We're looking at the south ring. You can't see the north pole in the middle, but this is the south ring, and there's a paper cone attached to the coil which is sitting in between the north and the south here. Okay, and you can just see here I've got it set on a frequency between 4 and 5 hertz, and it's a sort of sine wavy sort of input there. So the electrical signal just makes the cone move in and out. But if I change the frequency of the signal, I can make the cone move in and out faster, and I can produce different frequency sounds. And that is basically how your loudspeaker works.